All right, let's dive right in. You know how sometimes you look at a page of notes and it's so packed with formulas and terms you just don't know where to start? Well, that's exactly what we're tackling today. We're going to take a student's super dense physics cheat sheet and turn it into a guide that makes the basics of electricity crystal clear.
And here it is. This is our roadmap for today. It was created by a student named Srinivas, and he called it Student Friend We Will Pass. How great is that? Now, this isn't just some random list of formulas. It's a carefully crafted tool for success, and we're about to unlock its logic, step by step.
So, this really gets to the heart of it, right? How do we get past just trying to memorize all this stuff and actually understand what it all means? Well, that's our whole goal here today, to build a real intuitive understanding that's actually going to stick with you. So, where do we even begin? Let's start with the absolute basics, the building blocks. See, before we can get the big picture, we've got to get to know the individual players that make electricity happen in the first place. First up, we have electric charge. It's measured in something called coulombs. The easiest way to think about these is as the tiny individual particles of electricity, like single drops of water. They are the fundamental thing that everything else is built on. Okay, so what happens when those little charges, those drops of water, start to move? Well, that's what we call electric current, and we measure that in amperes, or amps. And our note here explains it perfectly. 1 amp is simply 1 coulomb of charge flowing past a certain point every single second. So it's not just about having the charge, it's all about how fast it's flowing. And to make this really, really clear, let's stick with an analogy. Picture a water pipe. The electric current is basically the amount of water that's gushing through that pipe every second. So more water per second, that means a stronger current. See? Simple, right? But wait, what makes the charge flow in the first place? It needs a push, right? That push is called potential difference, but you probably know it by its more common name, voltage. It's measured in volts, and it is the electrical pressure that gets the current moving. It's the energy that gets those little charges going. So let's go back to our water pipe. If the current is the amount of water flowing, then voltage is the water pressure. And it makes perfect sense. If you crank up the pressure, what happens? You're going to get more water flowing through that pipe every second. So more voltage means a bigger push, which leads to a stronger current. All right, so we've got our flow, and we've got the pressure that's driving it. Now let's get into the next part and see how this whole system is managed by a few simple but really, really powerful rules. Just about every system has some kind of friction, right? Well, in electricity, we call that resistance. It's measured in ohms, and it's basically anything that slows down or gets in the way of the current's flow. It's the obstacle in the circuit's path. Let's bring back our pipe analogy one last time, because it works perfectly here. A low-resistance circuit, that's like a big, wide, clean pipe. Water just flows through it super easily. But a high-resistance circuit is more like a narrow, kind of clogged-up pipe. The same amount of water pressure is going to result in a much, much weaker flow. Okay, so let's put all the pieces together. This slide really shows that crucial relationship. Let's say you keep the pressure, the voltage, exactly the same, but you make the pipe narrower, meaning you increase the resistance. What's going to happen to the flow? Well, it has to go down, right? And if you make the pipe wider, the flow increases. It's this beautiful, inverse relationship. And this all leads us to one of the most famous and important rules in all of physics, and it's right here on our student's note, Ohm's law. V equals I times R. Voltage equals current times resistance. It's just this elegant little formula that perfectly connects all three of the concepts we've just talked about. So what happens when all that electrical energy has to fight its way through resistance? Well, it doesn't just vanish. It actually gets converted into a different form of energy, heat. And that's explained by another rule called Joule's law. The more current you push through something and the higher its resistance, the more heat you're going to get. This isn't just some abstract formula. It's the reason your phone charger or your laptop brick gets warm when you use it. Now that heat we just talked about, that's a form of energy. But most of the time, we want to use electricity for more than just making things warm. We want to actually power things. So that brings us to the payoff. How do we measure the real work that electricity does for us? Well, that's where power and energy come into the picture. Electric power is measured in watts, and it tells us how quickly electrical energy is being used. So when you look at a light bulb and it says 60 watts, that number is describing its power, how fast it's consuming energy. It's the rate of doing work. But here's a really important difference.
Power is the rate you use energy. Think of it like your car's speed. But energy is the total amount you used over a period of time. That's like the total distance you drove. Your electricity bill doesn't charge you for how fast you used power, it charges you for the total amount. And the base unit for that is the joule. But since we use so much of it, our bills use a much bigger unit, the kilowatt hour. And one of those is a whopping 3.6 million joules. So let's wrap this all up by going back to where we started, our student's note. It's given us all the tools we need, but it also leaves us with a really powerful message about learning itself. And just like that, we've built our entire toolkit. We started with the basic particles and their flow, we learned the rules that govern them, like Ohm's law, and we saw how it all comes together to create the power that runs our world. These aren't just letters you have to memorize anymore. You now know they're the fundamental rules of how electricity works.
And hey, you might have spotted one other little thing on the original note, a quick mention of diopters, which is about the power of a lens. And that's just a great reminder of how huge the world of physics is. But for today, we absolutely mastered our mission, understanding the core of electricity. But you know, I think this is the most important part of the whole thing. At the very bottom of the page, Srinivas wrote, "Where there's a will, there's a way." And that's the real takeaway here, isn't it? The desire to understand, that will, is the most powerful tool you could ever have. So we'll leave you with this thought. We've decoded the map, we've gathered all the tools. The question is no longer if you can understand this stuff. The real question is, what are you going to do with that understanding? What will you build? What problem will you solve?